In this chapter, we will be learning a few more hypothesis tests, but they are of a different type. They are known as non-parametric hypothesis tests using non-parametric statistics. Now, to really understand what this means, let's focus on the word parameter. These first two ideas here of sample values being called statistics and population values being called parameters were a couple of ideas I introduced you to way back at the start of the course. For example, we used little n to make predictions for capital N. We used X bar to make predictions for mu. We used S, the sample standard deviation, to make predictions about the population standard deviation sigma. We have learned about P hat for making predictions about the population proportion P. We've even seen Y hat making predictions for a population regression line Y. Now, we are used to dealing with parameters. In all of these cases, we use these sample statistics in our hypothesis tests to make claims about these population parameters. And when we wrote our hypotheses out, HO and H1, we used either mu or P right here because these were the parameters we were making claims about. Well, in this chapter, we're not going to be looking at a single parameter, okay? And so we're going to be looking at all sorts of distributions or matrices, and it will be that is going to set it apart, and we will not be writing our hypotheses in the same way because we're dealing with non-parametric statistics. So you'll see what I mean as we dive in here. So here we go with the first example, and I really like this first example because it really is understandable. According to the Census Bureau, the marital status distribution of the US adult population is as follows. And you have the percentage in each of these four categories: single, married, widowed, and divorced. And then a random sample of 750 US males between 25 and 29 years old yields the following frequency distribution. In other words, this many people out of the 750. And it looks like we see a whole lot of singles and married. We don't see many widowed at all, nor divorced because they're still rather young in life. I mean, so we would think. So where the question is, at the 1% significance level, does it appear that the marital status distribution of all of these 25 to 9-year-old adult US males is different from that of the whole population? The key word here is we're not looking at a single category, we're looking at a whole distribution. Now, we could, if we wanted to, treat this as four separate one proportion z-tests. For example, we could say as a null hypothesis, let's focus on the singles category. We would say, oh, the proportion of singles is equal to 0.215 for 21.5%. And then we'd have an alternate hypothesis of either it is, isn't, greater than, whatever. Choose whatever inequality you want to, 0.215. And then we could take a sample proportion, which is really the 289 out of the 750 adult males. And that would be a way of testing just that one category, the single adults. However, we're not a single category. We're looking at the whole distribution of single, married, widowed, and divorced. And that's what sets this apart. Instead of doing four separate one proportion z-tests, we've got a single test that looks at the whole distribution. Okay, the following test is not available on the old TI graphing calculator. So if you've got an old TI 83 and you go into that menu, and let me show you what I mean by, well, I will in a little bit, by that menu, then if you don't see good enough to fit or GOF, then ouch, you're going to need to contact me and I will help you write a program that you'd have to type in manually. Now, most every test has assumptions, and for these chi-square problems, we are going to assume that all of the expected frequencies, not the actual frequencies, should be at least 5. And I'll show you what I mean by that. But notice how I'm writing the null and alternate hypothesis for this problem. I'm going to start by assuming that the distribution of marital status is the same for the 25 to 29-year-old males as it is for the adult population as a whole. And then we're going to show maybe that the distribution is different. Notice it's all about the distribution. Now, I've used and underlined the words same and different because that is a good way to help lock in which wording goes in the null and which wording goes in the alternate hypothesis. Now, we won't always use the words same and different, but they will be logically equivalent to that, as I will show you. Now, notice how these null and alternate hypotheses are not written with a parameter. There's no mu or p sitting there. These are written in words, which is typical of this type of problem. So in this type of problem, we're going to be entering our observed values into list 1. Well, these are the frequencies that we were given, and I've got written over here at the right that these are going to be what goes into list 1. Okay, then we're going to enter our expected values into list 2. Now, the expected values have not been given to us directly. We are going to have to calculate them using this formula E equals NP, just like the mu equals NP that we had back in the binomial chapter. And so what we're going to do is we're going to take the value of N, which is 750, because that's how many people were surveyed, and we're going to multiply each of those by their probabilities here. Now, notice in the widowed category, it was 7.7%, and I wrote this over here as 0.077. Don't forget to put that 0 in there, because without it, you're going to be treating it as 77%, and you've got to be careful with your calculator movements. So let's go to our calculator now. Okay, and I've already started typing in this data into list 1 and list 2. Now I've got down at the bottom of the screen the calculation that I used up in the highlighted cell, and you can actually just type in that multiplication problem, 750 times 0.215. When I hit enter, notice that's going to give me this 161.25. And so we are having to generate each of these on our own. Now, to do the goodness of fit test, we're going to hit stat, go over to our test menu, and scroll up from the bottom, and notice there's my chi-square goodness of fit test. I'm going to have to tell my calculator which list contains my observed values and which one contains the expected values. And then the place where we make the mistakes is right here with the degrees of freedom. It is 1 less than the number of categories. Since we had 4 categories in this problem, married, widowed, single, and divorced, 4 categories, we subtract 1 and get 3 for the degrees of freedom. Then when we hit calculate, out comes the chi-square and the p-value that we are interested in. Okay, so let's go back to our blue screen, excuse me, and let's check our assumptions. First off, I'm going to say that all of my expected values are at least 5. Once we did these 4 multiplication problems in list 2, all of those values were above 5, so the assumptions were not an issue. Then I'm going to state my significance level, and they said at the 1% significance level at the left. So there's my 0.01. And we've already seen on our calculator, these different values come out for chi-squared and p. At that point, we're ready to go. Notice how our p is going into scientific notation. Please don't miss that E-36, because that means move the decimal 36 places to the left. So we really have a lot of zeros before that 1 even comes up. This effectively, if rounding to 4 places, becomes a p-value of 0. So our decision is going to be, since our p is less than 0, reject the null hypothesis. And at the same time here, we're going to say the data strongly suggests, I'm using that word strongly because our p-value is way below 1%, that the marital status distribution differs between the two groups. And notice we were saying in the alternate hypothesis that it differs. Okay, let's go take a look a little bit more about what this goodness of fit is, yet again, looking at the data we've typed in. Whoops, I meant to show you all the calculator screen again, and that's where we had these values. But let's go back in and look at what we did here. We are looking at these numbers and we're saying, are these pretty much a match or not? Now we see that the 51.75 is what we were expecting and we got 53. I'd say there's a definite goodness of fit in that bottom category. However, we got a problem in this divorced or this widowed category. We were expecting 58 widowed people if the distribution of the 25 to 29-year-old guys matched that of the whole adult population. Well, you can see that that's not a very good match at all. Likewise, in the married category, we were off quite a bit. Actually, most of these categories, we were off quite a bit. And that's why in our conclusion, we said that the data strongly suggests that the marital status distribution differs. It's not the same. There's not a goodness of fit between the two different groups. Okay, let's continue on here. I've got another problem, and this one's totally different. A roulette wheel contains 18 red numbers, 18 black numbers, and 2 green numbers. Okay, basically there's 38 spaces on a roulette wheel, and the red and black go back and forth, evens and odds up to number 36, and then you've got the 0 and the 00 position, which are the green numbers. So at the 5% significance level, after we spin this 200 times, we want to see, is this thing in or out of balance? Okay, so here coming up with the hypotheses are a little bit weird because we don't have any probabilities. We just had, these are the results that came out. Now I'm going to say either in blue, the distribution is the same as what we expected, versus the distribution is different from what is expected. And that uses the words same and different, just like we had in the previous problem. And that might be a very comfortable way for you of writing the null and the alternate hypothesis. However, if we get into the vocabulary of the problem, it's asking, is the wheel out of balance? If the distribution is the same, if we are getting in our observed values what we were expecting, then the wheel is in balance. But if what we are observing does not match our expected values, then the wheel is out of balance. So if you're a little bit braver, you would use the vocabulary from the question itself and maybe go with the green way of writing the null and alternate hypothesis instead of the blue way. Now, when it comes to actually doing the calculations, you're going, whoa, I need the observed and the expected values. Let me show you how I went and calculated these out. This is a little bit of a different problem. I said to myself, here's the distribution of the different spaces as described in the paragraph. And there's 38 numbers altogether. Then I went to my calculator, and in list 1, I typed in the observed values. That's the frequencies, 88, 102, and 10. Then I went E equals NP to find my expected values. Well, I said we spun the wheel, the roulette wheel, 200 trials. There's my N. And then I put the probabilities, 18 out of 38, 18 out of 38, and 2 out of 38 as the probabilities that I multiplied together. And then when I did this and I went and ran this on the calculator, the goodness of fit, you can see the chi-square and the p-value. Now it turns out that it really wasn't that far off because our p-value is 0.58, and that says, because that's greater than alpha, do not reject HO. and therefore the data does not provide sufficient evidence that the wheel is out of balance. Now this one's a little bit different. I usually don't test on a question like this where you have to come up with the probabilities on your own. We usually like it better when the probabilities are given to you, like we were in that first example. Let's do one more problem of this type, because there's really several different patterns of these types of problems that can come up as you're working them. So here we go. I have my own Toei company this time. Toner Toys, a worldwide chain with stores in all 50 states, wanted to know whether sales were evenly distributed among the 5 weekdays, Monday through Friday. So for a sample of these days, and not included the holidays, here are the corporate records that were released in billions of dollars. At the 5% significance level, do the data suggest that the sales are evenly distributed throughout the week? Evenly distributed being, and we can almost at the end say, or not. Okay, now what does that mean? Well, we'll get into that in just a little bit, but let's take a look at how I wrote out the null and alternate hypothesis. I can say, oh, the values are about the same all week. There's that word same. And if I say that, I'm going to say the values are evenly distributed throughout the week. If the values are different throughout the week, then we'd say they are not evenly distributed throughout the week. In other words, is there one day of the week or so that really stands out head and shoulders above the rest? Or are they pretty much leveled out? That's what we're looking at. So again, we only have one set of values given here. These are our frequencies, and those are what are going to go into list 1. Now, coming up with list 2 is a little more challenging. If the data values are evenly distributed, that means they pretty much have the same value each day. So what I'm going to do is I'm going to take these 5 numbers, add them up and divide by 5. I'm going to find their mean. And if they are the same, roughly speaking, each day, we're going to expect $36.2 billion of sales each day. Notice I took the mean. I either added them up and divided by 5, or you type them into list 1, you do the one variable statistics to find X bar, and then you take that value and then type it in manually into that second column that way. So you have your choice. Okay, when we do that, first off, notice that all of our expected values are at least 5. They're all 36.2 for that problem. So the assumptions are met. And then when you go and do this on your calculator, the degrees of freedom is going to be 4 because there were 5 categories, and you can see the p and chi-square values that come out of the calculator. And our p-value is rather large. So since p is greater than alpha, we will not reject the null hypothesis, and the data does not provide sufficient evidence to suggest that the sales are not distributed evenly throughout the week. Now, as an English teacher, you'd probably cringe at this sentence because we've got this double negative, so it appears, but that actually is the way we want to word it. Because we're not going to say, oh, they aren't, or they are. We don't want to be declaring this is the way it is. We always leave our language soft, but the data does not provide sufficient evidence. That's how we begin a non-rejection. And then we always have the alternate hypothesis at the end, and our alternate hypothesis says they're not evenly distributed. And that's why those 2 nots, even though it doesn't sound like a great sentence, they are it is a good sentence, I'm trying to say. Now, I've given you 3 examples of the chi-square test, or this chi-square goodness of fit test. Pattern number 1, let's go back and look at this one more time, because I want you to see something that sometimes shows up. You are given frequencies, pretty much you have to be for every problem, but notice how these are all percentages. When one list is whole numbers and the other one is percentages, that's a pretty good clue that we are dealing with a goodness of fit problem. Also, when they mention the word distribution, that is another word that kind of sets this type of problem apart. When we move to this third category, evenly distributed or shows a preference for one day of the week, things like that are words that help you to identify this type of goodness of fit problem. Now, unfortunately, there are too many synonyms for me to be able to give you all the words that are possible for you to look at. So this just takes some practice, and every time you do a new problem, even in the review stuff for the final exam, you'll get some other wordings there, and you just add it to your list of things to watch for when you're doing these problems. Moving on, I want to follow up on that Plinko thing that I shared with you back when we learned the binomial distribution. You might remember that I was a little bit concerned at the St. Louis Science Museum that these distributions just weren't the way they should have been, and that it was out of balance. And I wanted to kind of close the door here, because I don't want any of you emailing me in 10 years going, Mr. Toner, I just thought about it. You never told us what happened with this Plinko machine. So let me show you, now that we have the mathematics, how I can test whether it is in balance or not. Okay, I took a close-up of all 3 pictures I had taken that day from that museum, and I physically went in and counted how many of these little ping pong balls fell into each of these different slots. And I filled them in on an Excel spreadsheet for the first, second, and third picture. And I found it rather interesting that there were 499 of those little ping pong balls. I think they intended to have 500 of them, but one must have gotten lost in transit or broken or something. So I said to myself, I'm probably going to get better data if I lump all 3 of these outcomes together. So in my spreadsheet, I added straight down, and that's what the 4th row is out of almost 1,500 of these balls. And then I said, let me calculate what I would expect to be those numbers. And I did the following calculation. I did binomial PDF. Okay, that was the one where we're finding the probability that X equals something. And I said there were 8 trials. Okay, there were 8 different times it could bounce to the left or to the right in that picture. There was a 1/2 chance of it going to the left versus right at each little stage in that game, if it's in balance. And then I left this last number off. Let me show you this on the calculator, what actually happens here. So I'm going to quit out of this screen that we just did, and I'm going to go into my second distributions, and I'm going to go into, not the second distribution, sorry. Yeah, I am going into there, sorry. Binomial PDF, and I'm going to say there were 8 trials, a 0.5 chance of going each way, and I'm going to leave off that 3rd number. When I do that, I get a whole distribution, and the first one stands for the probability of X equals 0, then the probability of X equals 1, then the probability of X equals 2. And I actually cheated. I took this and I hit store, that red button, and I stored it into list 1, just like that. And I don't see much here, but now if I hit stat edit, look what happens. All those probabilities went into list 1. And then I'd go to the top of list 2 and I'd say, this is going to be 1497 times what's in list 1. And I hit enter, and that gave me all those expected values that you saw on that bottom line of the chart. So that's kind of an interesting way. You are not responsible for knowing how to store a list outcome into there using that store key, but I'm just showing you something extra you can do and how I did this. And then I said, okay, looky here. I can compare these expected values. This one is pretty spot on in this category. Look at that. We were only off by 1.5 marbles. And this one, whoa, spot on there, pretty good. We were even doing pretty well over here and over there on the far left. But in that center, we were off by about 29 in that category. We were off by about 30 there. And so I'm going, I'm not super comfortable with a couple of these being way off. And that's why I thought, I better check this. So I ran this as a goodness of fit to see if the expected values and the actual values matched up with each other, whether there was a goodness of fit. And when I did this based on all 3 rolls together, take your 2 fingers, do a little drum roll on the desk in front of you here. And it turned out that my p-value was 0.1582. I can almost be 85% confident that it was out of balance, but I'm not reaching that 95% level I would have liked, or even higher if I were to call back to the museum and say, hey, you guys messed up in hanging this thing. So I had another great idea, and I said, it's really this third picture that bugged me even more so than the other 2. So maybe instead of lumping all 3 together, I could look at just the 3rd row. And I thought maybe that'll give me the result I need. And then it actually got worse, okay? I can only be 77% confident that the thing is out of balance, whereas previously I could be closer to 85% confident. So bottom line, end of the story here, the thing probably is a little bit off of balance, but I don't have enough evidence to really call them up and say, you guys goofed, okay? Let's move on. Now we turn our attention to another type of test called the chi-square independence test. And I'm using the same expected values here, the same assumptions. All expected values should be at least 5. And this time when you are doing these problems, again, the null and the alternate hypothesis are in words. But notice I'm using words such as not associated versus associated, independent versus dependent. The words associated or dependent will always go with H1, and not associated or independent will always go with HO. Notice how not associated has the word not in there, and we are used to not equal to being in the alternate hypothesis. So these are reversed a little bit for you. So null hypothesis, alternate hypothesis comes first. You're used to step 2, decide on your significance level. Then we're going to enter our data values into a matrix. That's something new. And the rest pretty much just falls into place. So let's look at this first example, and I'm going to walk through and show you how to use your calculator for matrices. The Gallup organization conducts periodic surveys to gauge the support of U.S. adults on regional primary elections, as opposed to state-by-state elections. The question asked is, it has been proposed that 4 individual primaries be held in different weeks of June during presidential election years. Does this sound like a good idea or a poor idea? And here is a contingency table for responses by political affiliation. In other words, we have a variable along the sides of what their political party is, and then we've got a matrix of their opinions, good idea, poor idea, no opinion, there. And we want to know, top of the next column here, at the 5% significance level, do the data set suggest that the feelings of adults on the issues of a regional primary are dependent, there's our key word that kind of helps us out there, on political affiliation. And so my alternate hypothesis this time is going to be, well, first off, opinions are independent of political affiliation will be the null, and opinions and political affiliation are dependent on each other in the alternate hypothesis, using those same words that you see just there to the left. Now our significance level is going to be the 5% that it says right up there in the paragraph. And then now we've got a whole new procedure of entering our values into a matrix category of our calculator. So I'm going to talk through what I've got right here, but if you want to pause and read it, that's fine. We are going into a new area in our calculator. So I'm going to turn our calculator on here, and I'm going to quit out of here for a moment, and we're going to hit second, and then above the x to the minus first key. Where is that? There you go. You see the word matrix above that red key? We're going to go there, and then we're going to go over to the right to edit matrix A, and I'm going to hit enter. And at that point, these top numbers allow me to adjust the size of the matrix. For example, if I change that first number to a 4, I now have 4 rows. Notice how that bottom row of 4s showed up. If I go back and change it to a 3, so I can gauge the grid size there to match the size of the matrix. And I've then just gone in and entered all these different numbers in that you see on this problem. After you have entered these in, you are then going to hit your stat button. You're going to hit, go over to the test column, and then right near the bottom, you have the chi-square test, also known as the chi-squared independence test. When you choose that option, you tell it where the matrix is. Now, my data is in matrix A, and you probably saw earlier, there was nothing in matrix B. I can tell it where I want the expected values to go. And if I wanted to change this from B to something else, I would hit second matrix, and I could then go and say, I want to choose B, hit enter, and there's my matrix B going into that position. Now that's all you have to do, and hit calculate, and out comes these values. You are told what the degrees of freedom are here. You don't need to enter that in yourself. You just need that chi-square and p-value that are showing up on the screen. So let's go back to this right here. I'm showing you where it was on the calculator. It's always the first number is rows, the second number is columns, and so you can adjust the different size. And I showed you already the test statistic and the p-value that come out are right here. Now, as far as checking the assumptions, we needed to check that all the expected frequencies should be at least 5. Now, when we ran the chi-square test, and I'm going to do that again, I hit stat, go over to tests, go up from the bottom to chi-square test. It asked us, where should we put the expected values? And it will overwrite anything that is in that matrix B position for me. And even if it was empty or not even existent, it will create matrix B and put those expected values there when I run this chi-square test. Now, to check those values, the easiest way to do this is to hit second matrix, go into matrix again, go over to the right to the edit column as if you wanted to edit the matrix, and go down to choice B. Because at that point, when you hit enter, you can now look at all of those expected values, and you can inspect them and see that, yes, all of them are above 5. And that's what our assumptions were saying. So let's go back to our problem here. And I've already checked the assumptions. I'm going to say all of them are met. All the expected values are at least 5. So at this point, we move on and we say that our p-value of 0.4 is greater than alpha. We will not reject the null hypothesis, and the data does not provide sufficient evidence to show that political opinions and political affiliations are dependent on each other. Okay, it's really not that hard of a test once you recognize what type of test it is. It's just a matter of learning how to go in and enter those values into the matrix after having recognized it's one of these types of problems. Let's take a look at a second problem here. In this second problem, it says that the American Bar Association publishes information on lawyer characteristics. And the following contingency table cross-classifies 300 randomly selected lawyers by status in practice. That's the type of practice we see over here at the left, and the size of the city. Under 250,000, over 500,000, etc. So that's how many of the lawyers are in the different categories. Do the data provide evidence to conclude that the characteristics, size of city, and status in practice are statistically dependent? Notice that this is not 3 separate lists that you are given. It's actually a matrix. And you can tell that because they've given you these variables. You know that this is the status and the practice on the left, and you've got the size of the city at the top. And so those 2 variables or classifications help you to know that it's just not 3 columns that we're comparing here. It's a whole distribution. And again, we need to write our null and our alternate hypothesis in words. So I'm going to say the size of the city and the status and the practice are either independent for the null hypothesis or dependent for the alternate hypothesis. Now, I've already entered these numbers into a calculator, into the matrix area. I then went and ran the chi-square test. And let me show you what matrix B looks like. Matrix B has these numbers in them. I'm going to make that a little bit bigger for us to look at, like that. And when you actually look at this now, you'll see that we've got several small numbers. Notice there are 2 numbers in the second column that are underneath 5. And then I've got this 3.6906 in the third column that is beneath 5. 3 of those 12 numbers are below 5. Now we maybe could get by with 1 of those being below 5, but I'm going to say 3 of the expected values are below 5. Even though our calculator, when you run the chi-square test, says here's chi-square, here's p-value, still it's just doing a mathematical exercise. It doesn't know to check the assumptions, and on our own we're just supposed to go, we have a problem, Houston. And we don't finish the test. We just say consult a statistician. Okay, that basically means we're going to need to use some higher powered type of a test that we don't know in this course that we're leaving for later. Now, I will not give this to you on your test, on your final exam, because I'm not cruel, but I want you to be aware of it. Okay. Really, the only assumptions I'm majorly checking on your final exam is the normality assumption that's associated with the t-test. But I want you to be aware of these assumptions, even though they won't be violated on your exam. Let's do 1 more of these problems so we get an example of another good one that actually works. In 1989, roughly 58 million Americans suffered injuries. More males were injured than females. These statistics do not tell us whether males and females tend to be injured, however, in certain circumstances. Maybe that is a lurking variable here. So one set of categories commonly used for accident circumstances is while at work, home, motor vehicle, and other. In order to decide whether there is an association, another key word that piques my attention, between accident circumstances and sex, a safety official in a large city took a random sample of accident reports and he found this data as you see in the table. So do the data provide sufficient evidence to conclude that in this city, accident circumstances and sex are statistically dependent? So I switched from the word associated to dependent, but okay, that's fine. They're kind of in that same vein. You can use either one of these words for these types of problems. And so perform the required hypothesis test. So I'm going to say these two variables are independent for the null hypothesis and dependent for the alternate hypothesis. Okay, so it helps you to know, and maybe this might be something you put on your cheat sheet for your test, that in your HO, you are using the word independent, whereas in H1, we would have dependent. We also saw earlier that the word associated would be an alternate, and not associated would be in the null hypothesis. And I'm also going to throw in the words related and not related, because those are another pair of words that show up in these types of problems. Okay, so how do we do this? Again, we are entering these numbers that are inside that table here into our matrix portion of our calculator. At that point, we then go and we run our chi-square test, and I've already found those values there for you. The calculator tells you what that degrees of freedom is. At that point, we then go check our expected values, and I've got these listed here, and I'm just saying that one of them is below 5. That's this 4.24657. But I'm willing to accept 1 out of the 8. Okay, but if there was a second or third, then I'd say, yeah, I've got some problems here. And now let's go back to our p-value, which ended up being 0.0341. It was under alpha. So since p was under alpha, reject HO, and the data seems to suggest that accident, circumstances, and sex are dependent. Now we just say they're dependent or they're not. We don't actually start editorializing saying, oh, a guy is more likely to get injured in this type of situation and a woman's more likely to get injured here. We don't go there. We just say related, not related. Okay, so that is the chi-square independence test. Now we've got one more type of test, which is called the one-way analysis of variance. And analysis of variance has that acronym, which becomes ANOVA. And it is used to compare, as it says, the mean of several populations. Let me draw something down here in the corner here. Once you know that we're dealing with means, if you have one mean, you know that you're going to be dealing with the t-test. If you have two means, you're either dealing with a paired t or you're dealing with a two-sample t. Now I'm telling you, if you have 3 or more means, that's where the ANOVA test comes in. So I wanted to relate this to something you already understand. Now, as far as these assumptions, these are pretty straightforward. We're not going to be testing these assumptions, but we're going to be assuming that we have 5 independent populations and that the data has been gathered by some randomized type of design. Each population, the variable is going to be assumed to be normally distributed, so we would have to check that. And we would assume that the standard deviation is about the same for each of the 3 populations. Okay, so this is going to be the process we're going to use on each of the different hypothesis tests. And I'm not going to go over it right here because I have it reprinted on the next screen right next to the first problem we're going to do. So here we go. Manufacturers of golf balls seem to always claim that their ball goes furthest. So 20 golf pros are randomly selected to test 5 brands with 4 golf pros per brand. Here are the results of each drive in yards. So I've got 5 different brands, 4 numbers in each of those columns there. And I don't have to have the same number in each column, but it just happens that I do. And the question says, do the data provide sufficient evidence to conclude that a difference in mean driving distances exists? Well, first off, the word mean is involved. And then when you see that we've got 5 different brands, that really tells you, ooh, 5 different lists I'm going to need to type my values into. Now, when it comes to writing down the hypotheses, I told you to have these steps here listed off to the side. We write our null and our alternate hypothesis. Now, this is a borderline parametric test, but we can't write the hypothesis the same way. We're going to begin by saying mu1 equals mu2 equals mu3 equals mu4 equals mu5 equals however many means are involved, however many lists we have. And then we say in words, the means are not equal. Okay, we do not say mu1 not equal to mu2 not equal to mu3, etc. That is bad logic, and we do not do it because it can get you into some issues here. For example, let me just explain in a very simple way. If I told you that 8 was not equal to 10, you would agree. Those numbers are different. But if I then told you 10 is not equal to 8, doesn't that open the door that the first and the third number are the same? And we get into some logic issues there. And that's why we always just in words say all means are not equal. Then we move on here and we say, okay, here's our significance level. They told us to use alpha is 0.5. And then what we need to do is we need to type these into our calculator. Now I'm going to pause the video for just a moment while I type them in. Now, after you have typed all of these into your calculator, you now are going to go to the bottom of your test menu where it says ANOVA, hit enter, and then it's just going to give you an open parentheses and you need to know what to do. You are going to say second L1, comma, second L2, comma, second L3, comma, second L4, comma, second L5. However many lists you did, you need to tell the calculator, these are the lists that I'm working with. After that, you're going to hit enter, and I've already got this on the screen now, and you are going to get, let me see if that's showing up here. Well, it's not showing up here. You are going to get a listing. Let me go back to my calculator. Let me not go back to my calculator. Bottom line is, it's going to give you some numbers. And the first number that you see is what's called the F statistic. And I would write that down in the top right corner of this table and right beneath the word F statistic. It then gives you the p-value. Now, for most of us, that's all we need, right? Because with the p-value, we can make our decision. And that F statistic, that's like a t-value or a z-value or a chi-square value. It's just a different distribution we're using this time, okay? And then it gives you some more numbers. And after, when you start looking at it, the calculator says, treatment followed by 3 numbers. And those numbers are 4, 458.5, 114.625. Then it says error followed by 3 numbers, which you write down. And then we manually add down these next 2 columns to fill in those last 2 spaces. Now, you'll notice that I have in this table the word factor and error because that's what your calculator is using. But typically, the key word that we're supposed to be using is the word treatment. If you leave our class and you start moving on to other classes, this position that I'm pointing here to with my mouse in the SS column, which stands for sum of squares, and in the treatment row, SS, TR, sister. Then we get Mr. And in the next row, we have Sissy and Missy. And then we have assist, I guess, but then F is equal to Mr. over Missy. And so you've got all these different abbreviations with the TR, which is part of the lingo that's used when you leave this class. Now, why do you have to fill in this table? I hate to tell you, kind of the answer is because I'm supposed to teach you how to fill in this table, and other teachers, when you start using this in other subject areas, I know we're using this in biology, I know we're using this in advanced the psychological statistics course. At those points, they will teach you how to read these tables and what some of these numbers actually mean. I've had some students who have used this in other classes before come alive at this point and they say, oh yeah, this means this, and I didn't take notes because I know I don't need to really explain this to you, but it will be treated or taught to you at those places when you need them. For now, I'm just supposed to show you how to fill out this chart. And quite honestly, when we test on this, I don't want to show you a chart because that gives you it away that this is an ANOVA problem. So instead, I'm usually just asking you to tell me what's the test statistic, what's that F statistic, or what's the p-value, just like we do on the other hypothesis tests. I want you to be able to identify this as an ANOVA test because you see that we're dealing with means and you see that we have more than two populations. Those are the dead giveaways that were in this category. At this point, you're just going to take that p-value and say, okay, p is greater than alpha, do not reject HO, and the data does not provide sufficient evidence that the means are not the same. Again, notice our sentence seems a little bit awkward having two nots in there, but technically it is worded the way I do want to have it worded. It is technically correct that way, logically speaking. Now I've got this comment here because our tendency is to ask the question, well, which brand of golf balls is the best? And I said, note that the ANOVA test cannot tell you which brand drives the farthest. It only tells you whether a difference exists in the mean driving distances. Just is there one that's, are they not all in balance, or are they together? And that's what kind of makes it more like a non-parametric type of problem. Okay, let's take a look at one more problem of this type, and then we will, I think that's the end after that. Yep, so here we go. A chain of convenience stores wants to test 3 different advertising policies, and here they are. And then it says 18 stores were randomly selected and divided into 3 groups of 6 stores each. Each group used one of these 3 policies. Following the implementation of the policies, sales figures were obtained by each of the stores during a 1-month period, and here we have it. Actually, once you know it's an ANOVA problem, you almost don't even need to read the problem because the context doesn't even come into the very, very last line. So at the 1% significance level, do the data provide evidence of a difference in means? So you know you're dealing with means. You see that you have 3 lists over here. That's the clue that tells you this is an ANOVA problem. And I'm going to, again, begin with mu1 equals mu2 equals mu3. I stopped at mu3, and then alternately, I'm going to say the means are not the same. I'm going to enter this into 3 lists on my calculator. I'm going to go to the bottom test. In that test menu, choose ANOVA. It's going to open the parentheses. I'm going to type in L1, comma, L2, comma, L3. When I do that, it's going to spit some numbers out to me, okay, including this p-value over here. At the top of the list, it's going to tell you that our test statistic, if I can find my mouse, there it is 8.5338 with our p-value there. And then you're just going to read the next row coming out, read the next row coming out, and then just add down in those 2 columns. And then look at that p-value. It's very, very small. And so since p is less than alpha, we will reject the null hypothesis. And then we will say the data strongly suggests that the means are not the same. And if you actually look at the data, you can kind of tell that they're not the same, because it kind of makes sense that if you're using circulars and advertising in the neighborhoods, you should be getting better results with that more advertising. Here's our 31, our 32, and our 29, and there are no numbers even that high in these first two lists. And even the 27 is higher than these other two lists, but it's not asking us which policy is best. Okay, that's kind of obvious here. We're just asking, is there a difference between the means or not?